Hello and welcome to the second part of my talk on positive scalar curvature from a concordance viewpoint. In the last talk, I have shown you the construction of a comparison set for the space of all please C metrics. And the nice thing about this comparison set is that it only encodes concordance information of Riemannian metrics within its homotopy type. And we have also seen that this cubical set is a Kant set. It's a good cubical set. So this allows us to throw the entire combinatorial theory of cubical set to its space. And for example, this allows us to give a really convenient and element-wise description of its homotopy groups. Instead of taking the geometric realization and then the maps from Sn into this incredibly huge CW complex, we can describe its homotopy groups by equivalence classes of elements with a certain property. And this is really nice if we want to find non-trivial elements, because this allows us to write down good candidates more efficiently. We have also seen how the original space of PSC metrics and the approximation space are related. We have constructed a so-called suspension map that assigns to a map of Riemannian metrics its adjoint metric. But we couldn't have used the whole combinatorial version of the space of PSD metrics. We needed it to restrict towards a smaller cubical subset that is weakly homotopy equivalent, and where the maps satisfy a certain speed constraint so that we end up in the right target. This happened in the last video, and in this video, I would like to have a look at the index theoretic counterpart of the story. So when I do index theory, I usually work in the following setup. I consider a Riemannian manifold, usually complete, and I assume that this manifold is spin. So this means this is even more than oriented. It is a manifold is spin if it's oriented and if its second Stiefel-Whitney class also vanishes. This is more than just an orientation. The reason why we are interested in spin manifolds is that the spin condition allows us to construct a spinor bundle over it. And in fact, this is equivalent. If you have a spinor bundle of this kind, then you also know that your manifold is spin. Since I work in the Clifford linear setup, my spinor bundle is always graded, independent of the dimension of the manifold. That means it decomposes into the subbundle of so-called positive spinors and into the subbundle of so-called negative spinors. And we also have right action by the Clifford algebra in the degree, the dimension of the manifold. The reason why we are interested in spinor bundles is that there is that there is a nice operator acting on the section of this bundle, namely the Dirac operator. This is a first order linear self-adjoint and elliptic operator, which is also Clifford linear, because I work in a Clifford linear setup. The reason why we are considering the Dirac operator is its close connection to the scalar curvature on its underlying Riemannian metric, the metric we use to define it. Namely, the Bochner-Lichnerowicz-Schrödinger-Weizenburg formula tells us that the square of the Dirac operator equals the connection Laplacian plus 1/4 of the scalar curvature. Since the connection Laplacian is non-negative, this formula implies that the square of the Dirac operator is invertible if the scalar curvature is positive. Hence, also the Dirac operator is invertible. On the other hand, since the Dirac operator is Clifford linear, its kernel generates a K-theory class. And the famous Atiyah-Singer index theorem actually implies that this K-theory class is independent of the Riemannian metric we use to construct the Dirac operator. It's a solely topological quantity. These two information produce a very effective obstruction against positive scalar curvature, because if the scalar curvature is positive, then the Dirac operator is invertible, its kernel is trivial, and hence its class in K-theory must be 0. On the other hand, if we know for some reason that this class is non-zero because of, for example, the topological description, when we have an obstruction against positive scalar curvature. Okay, but as I told you also in the previous video, I'm not so much interested about the existence question. I'm more into secondary questions, and therefore I would like to modify this setup to obstruct homotopics relating generator to the trivial element of a homotopic group. And in order to do that, I need a convenient description of the classifying space of the K-theory, and this was luckily provided to us by Johannes Ebert. He observed that the space of all pseudo-Dirac operators is a classifying space for real K-theory. So let me recall what a pseudo-Dirac operator is. A pseudo-Dirac operator, or basically the set of all pseudo-Dirac operators, is a set over the space of all Riemannian metrics. And well, its fiber consists of all pseudo-Dirac operators on the spinor bundle that is produced with the help of a Riemannian metric G. So the pseudo-Dirac operator there, the pseudo-Dirac operator with respect to Riemannian metric G, is a pseudo-differential operator of order 1 that is Clifford linear, self-adjoint, odd, and whose principal symbol agrees with the principal symbol of the Dirac operator of its underlying metric. Notice that this pseudo-differential operator is an operator on the sections of the bundle spinor of G. This bundle depends on the metric G. Its isomorphism type is independent, but the precise isomorphism is not canonical. So you can construct isomorphisms, but they're, so to say, not the identity. Yeah. And yeah, as I told you, if our manifold is closed and if this set is not empty, so for example, if our manifold carries a positive scalar curvature metric, then the space of all pseudo-Dirac operators is a classifying space for real K-theory. That means that the homotopic classes of continuous maps from a certain space X into the space of all pseudo-Dirac operators is in bijection to the real K-theory group of our topological space X. This is a result of Johannes Ebert. And even better, this isomorphism is not just an abstract natural one, but it is actually given by the index difference, by the operator index difference. So this is a really nice black box we can use here, because with that result, we have a really nice cubical model for the classifying space of real K-theory, which is, again, given by a nice adaptation of a singular set of a topological space. So here we consider the cubical set of all smooth block maps from Rn into the space of all pseudo-Dirac operators. The phase and degeneracy maps are, as in the case of the cubical model for the space of PSC metrics. Yeah. The nice thing about the previous result is that the index difference has now a really convenient description, namely it is the cubical map from the combinatorial model of the space of PSC matrix towards the cubical set, towards the combinatorial model of the space of invertible pseudo-Dirac operators, which is given by assigning a Riemannian metric its Dirac operator. Yeah. Look how neat this map is. There is no identifications involved, and you can write this down absolutely explicitly. Okay, so this is therefore, let me therefore summarize our achievements from the previous video and this one. We have constructed the space, the approximation space for the space of PSC matrix, which is the geometric realization of the cubical set of all PSC block metrics. And we have related it to the combinatorial version of the space of PSC matrix via the suspension map. As I told you at the beginning, this map is only well defined on the weakly equivalent cubical subset. This is the reason why I used this dashed arrow here. And we have just given a nice description, a nice model for the index difference from the space of PSC matrix to the classifying space of real K-theory, which with our appropriate model is just given by the map that assigns a Riemannian metric its Dirac operator. So ideally, to prove a factorization result, we would like to have a map from here to here, but this is difficult because if such a map exists, it must at least have a complicated description, because an element of the nth layer of this cubical set is given by a family of operators, of invertible operators on M, while an element of the nth layer in this cubic set is given by a single metric on M times Rn. So there's a kind of a mismatch. Therefore, it is better to construct a different model for real K-theory, which sits then here in the lower right corner, which is big enough to host this model, and also that allows a convenient description here. And the strategy to construct this model is just the same strategy we used to construct this cubical set out of this topological space, namely by blockifying Riemannian metrics. And in the same manner, we will, so to say, blockify invertible pseudo-Dirac operators with this strategy. Okay, so blockifying concepts means we need to introduce more notation, and in this case, it's the notation of a block Dirac operator. So this is now quite a dense slide, but let me go through it. If we have given a Riemannian block metric on M times Rn, we call a pseudo-Dirac operator on this spinor bundle, a Clifford-linear pseudo-Dirac operator on the spinor bundle constructed by this block metric. We call such an operator a block Dirac operator if it is sufficiently local. This is what the first condition says, without going into much detail. But more importantly is the second condition, which says that outside unknownly large cube, this operator decomposes in the same manner as the Dirac operator of a product metric would do. Yeah, recall that a block metric decomposes into a product metric outside a certain sufficiently but unknownly large cube. And we require that pseudo-Dirac operator is behaves in the same manner. So this is what the second bullet point tells you. And again, all of these, we can take the set of all these operators and they together assemble to a cubical set. So we have, again, phase and degeneracy maps here, which I will not write down. And well, with this cubical set here also comes with two canonical maps, namely the map that assigns to a block debug operator P its underlying block metric G, and we also have a section of this map, namely the map that assigns to a block metric its debug operator. Okay, so this is a block debug operator, and now the new model for our real K-theory consists now of the cubical set of all invertible block debug operators. And this is now in calculation that this is indeed a cubical subset. So the phase and degeneracy maps that come from the bigger model, the phase and degeneracy maps that come from the cubical set of our block debug operators actually preserve the invertibility condition. And yeah, this is true, fortunately. And if we restrict the debug operator map to the cubical set of all PSC block metrics, then we'll actually land in the space in the cubical set of all invertible debug operators. Okay, so this is kind of analogy of the previous video. We have, so to say, blockified the space of all invertible debug operators. And as before, we would like to connect it to the original space. And this is done by the operator theoric analog of the suspension map from the previous video, the so-called operator suspension map. And what this map does is it takes a smooth block map of invertible pseudo-debug operators and assigns it, so to say, its adjoint operator on the spinor bundle of its adjoint metric. And this is the precise formula here. I wrote them down for completeness, but yeah. And again, you can actually show that this suspension map commutes with the connecting maps. So it's a cubical map. And the same problem as for PSC metrics again occurs here. The problem is that the operator theoretic suspension map does not have the right target. It only takes a family of invertible pseudo-debug operators to a single block debug operator without the invertibility condition. Because as for the scalar curvature metrics, if the parameter runs too fast, then you might lose the invertibility condition. This can happen here as well. So this is unfortunate, but luckily we can come around that. Namely, we can find, as for scalar curvature metrics, we can also find a nice cubical subset of this space in the cubical set of all pseudo-debug operators, such that the suspension restricts to a map with values in invertible block debug. This cubical set has a nice property that if we restrict the suspension towards this nice cubical set with the correct speed constraints, then it indeed lands in the cubical set of all invertible block debug operators. And we can also choose this space B and A in such a way that the debug operator maps this cubical subset to this cubic subset. So I should mention that these cubical subsets A and B, they are far from being unique. These are just cubic sets that are the block maps are parameterized sufficiently slow. So the speed constraints you write down, they are far from being unique, but if you have matching ones, then this is good enough. So more important thing is that if you have nice speed constraints, you need to have the correct speed constraints so that you do not lose any information. So you also want that the inclusions are weak homotopy equivalences. This can be achieved. And in the end, it turns out that this diagram commutes up to homotopy. So this is the main result of my talk. And it's in fact twofold. Namely, the first statement is that this diagram commutes up to homotopy. And the second part of the statement is that this operator theoric suspension map is a weak homotopy equivalence. So, I mean, I told you that the cubical set of all invertible block Dirac operators is, so to say, a model for K-theory, but this requires a proof. And this weak equivalence statement is precisely the argument. This is also a classifying space for real K-theory, because we know that this is a classifying space for real K-theory. And we have a zigzag of weak equivalences. Yeah, so the weak equivalence statement says that the block Dirac operators form a classifying space for real K-theory, and the homotopy commutative statement shows that the suspension maps that the homotopy commutativity says that the Dirac operator here and here these Dirac operators models the two kinds of the index difference. This Dirac operator here and here is a version for the index difference, for the Hitchin index difference. And this Dirac operator description is, so to say, a version for the Gromov-Lawson index difference. So the homotopy commutativity of this diagram shows that these two versions of the index difference agrees. This is what you should take away from the theorem here. And let me shortly go over the proof. I will not prove only the weak equivalence statement here. The homotopy commutativity is a bunch of calculations, basically. To show that the space of to show that the operator suspension map is weak homotopy equivalence, we need to show that it induces an isomorphism on all homotopy groups. And in order to do that, we push it forward to KK theory. Here, the upper horizontal map, this is a well-known map written down by Kasparov in his paper. This is kind of a bounded transformation. And so we take elements in the K theory group here. And also this right vertical map is a well-known map for operator theorists. Namely, this is the Kasparov product with the fundamental class of K homology. This is, so to say, the Kasparov product with a fixed KK element from which Kasparov proved to be an isomorphism. So this is well known, classical. So the remaining tasks are now the following four ones. First, we need to construct the lower horizontal map, which is kind of analogous to the upper horizontal map. Then we need to show that this diagram in fact commutes. This involves the calculation of the Kasparov product. And then we need to calculate these homotopy groups by hand. And if you do it, you will notice that this group here actually has the same groups as all the other three groups here, because these are, so to say, K-free groups of a point. And then you see by some algebraic tricks that since this map here and here is an isomorphism, this map must be surjective. And since K-free groups are cyclic of order 1, then a surjective map between two isomorphic groups, you deduce from the fact that group homomorphism between two isomorphic cyclic groups, that a surjective group homomorphism between two cyclic isomorphic groups must be an isomorphism. From that fact, you deduce that the lower horizontal map is also an isomorphism. And now you have a commutative diagram where 3 out of 4 morphisms are isomorphisms. So the last morphism must also be an isomorphism, which concludes that the operator theoretic suspension is an isomorphism. And that finishes the proof and in fact my talk. So let me shortly remind you what we have seen in the 2 videos. We have constructed a comparison space to the space of all PSC metrics. We have done the same thing for the classifying space of K-theory. Namely, we have constructed a model based off invertible block Dirac operators. And we used this model to factor the index difference over the space, because this convenient model allowed us to identify the index difference of Fitchen and the index difference of Gromov-Lawson as cubical maps that assign to Riemannian matrix its Dirac operator. This is the interpretation here. And with that description, it was not so hard to prove that these diagrams commute up to homotopy. So I hope you enjoyed my talk, and I would like to thank you for your attention and hopefully see you soon. Bye-bye.